Hi, welcome back. This week we're going to talk about Chapter 9, Classification and Regression Trees, or otherwise known as CART. This is one of the three pillars of data mining, along with logistic regression and neural networks. Like neural networks, we can use this to make classification and predictions. And the basic idea here is that we're going to come up with some goal that we want to accomplish, classify a record as will accept a credit card or will not accept a credit card, for example, and then come up with a bunch of rules that describe all potential data points. So those rules might say if income is greater than 99 and education is 1 and family is less than 3, then the probability that someone is going to accept the credit card offer is 0.0077, so we would classify such individuals as a non-acceptor. We use trees to describe what's going on here, and this tree, this node right here, this terminal node, corresponds to this rule right here. So let's break this down. We see we have 5,000 data points and 4,520 are zeros, 480 are ones, so we see the proportion or the probability and rate associated with those things. And then we will say if income is less than 99, that's going to be our first split. So if income is less than 99, we have 99% zeros, or 3,718 zeros and 36 ones. So this is what we call a terminal node because it doesn't go anywhere from there. You might also call it a leaf if you're going to use the tree vernacular. If income is greater than 99, then we can see that we're not done. We have another split coming off of that node, and we split if education is 2 or 3, in which case we would say there's a 75.31% chance that someone's going to accept the loan, and otherwise if education is 1, then there is a 10% chance that somebody's going to accept the loan. And we're not done here. You can see this is not a terminal node. We split one more time and say if family is less than 3, then we are in this terminal node right here, family less than 3. Probability of success is 0.0077. There are only 5 ones in that group out of whatever that turns out to be, 668. And so that matches this rule that we have here. And you see there are other rules. Everywhere we have a terminal node, there's a rule. And if family is greater than 3, everything else being the same, then there's a high probability of them accepting, so 79.17%. So the key ideas that we have here are, first of all, recursive partitioning, where we continually split the records into 2 subsets to achieve the maximum similarity within each new subset, which is the same thing stated differently when we say that we have the greatest dissimilarity between the subsets. That's one way that this is done. Another way that this is done is by pruning the tree, and basically what happens there is full-grown tree is used so that all of the nodes are in agreement as much as possible, and then you can think of those as leaves on a tree, and then the tree branches are cut off to make the structure more simple, and we do this to avoid overfitting, and we'll talk more about that a little bit later. In the case of recursive partitioning, basically what we're going to do is we're going to select one of the variables, call it xi, and then we're going to pick a value, si, that divides the data into 2 sets, not necessarily equal, and measures how dissimilar each of the sets are, and and then we're going to do that again with maybe the same variable xi, or could be a different variable xi, and we're going to then pick a different value to split on, and again try to maximize the dissimilarity in the groups. And after the first split, then we're going to repeat that process over and over and over again until we hit a stopping rule. So this idea can be accomplished with continuous data, but it can also be done on categorical data. So imagine you had a variable that had 3 different categories, A, B, and C. You could say how many ways can we split those into 2, and you can write those down, A by itself, B and C together, B by itself, A and C together, and so forth. And in this example where there's only 3 categories, it's not too difficult to write down, but when you have a large number of categories, this can be potentially a very large number of splits. If the data is categorical but ordinal, then that makes the number of splits a little bit more manageable, because we can't have say 1 and 3 together, for example, and 2 and 4, because these things are in order. So that's not going to be possible. It makes it a little bit more manageable. When we're splitting on continuous variables, the algorithm is going to split on the first value, measure the dissimilarity between the 2 subsets, and then split at the next value and continue. And it's going to do that same process repeated over and over and over again for all the other variables, and then whichever one gives the greatest dissimilarity is the one that is used for the split. So let's look at an example with our riding lawnmower data. We've seen this before. We have 24 households that either own or don't own riding lawnmowers, and we're going to try and predict or fit this classification tree using income and lot size as our predictor variables. Before we do any sort of splitting at all, we can note that there are 50% owners and 50% non-owners in the data set, and when we tell JMP to go ahead and find the best places to split, we see that down here income is the first one that we should split on, and the cut point is 85.5. Lot size would be the next place that a split comes would be recommended or would be optimal, and that would happen at a cut point of 20. And we can see that the income split is a better than a lot size split, at least initially, by looking at the candidate G squared value, and we see that whichever of those is highest is the one that is a better split. We can also look at the log worth, and whichever one of these is higher also indicates the better place to split. So in this case we see income split at 85.5 is a better place to split initially than lot size at 20. We see that when income is used as the first split, greater than 85.5, we have what we call a pure node, and that means that all of the members of that node have the same value. In this case, they would be owners. So that takes us to the next split, and the next split is going to be that's recommended is that we use a cut point on lot size of 20, and you can see that corresponds here. We've got the G squared, we've got the log worth, and here's the cut point. But notice that income is also showing up here, so we could split on income at 85.5 in the first split, and then split again on income if we like. And if we were to do that, they're saying JMP is telling us that 60 would be the best place to do that, but the candidate G squared and log worth both are smaller than what we have for lot size. So that tells us that lot size cut at 20 should be our next cut point. We can continue to do this, and when we do that, we see after 7 splits that we have this decision tree. So the first split was on income being less than 85.5 or greater than 85.5. And then we said let's split on lot size being greater than 20, being less than 20, and depending on which way we go, you can see all of the rules. So you take a data point, a new data point, and classify it according to this decision tree by simply following the income. If it's less than 85.5, then go this way. If it's greater than 85.5, then go that way and do whatever the recommendation is in that node. But you can follow this down. Eventually you're going to hit a terminal node of some sort where you're going to be predicting, or rather classifying according to the probability, which is not shown here, but in this case, for example, you'd see blue, which signifies 100%. So we have a pure node here, 100% of the values. It looks like there's only one, but 100% of those are classified as owners. So we use the notion of a tree because we have split points become the nodes on the tree, and whenever we have a terminal node, that means that we have a leaf and there's no further splits. It's important to keep in mind that the records in each of the nodes are from the training data set and not from the validation set. The validation set is used to not to build the tree, but to see how the tree does out of sample. And you'll also see that this is one place where we use a test data set as well, and you'll see why that is in a few minutes. We can get what's called a leaf report, which basically tells us all of the rules that we might possibly use in order to do classification and the probabilities associated with each of those. And this is important because anybody can understand this, and you can just take it to your boss or your manager, whoever it is at work that you want to explain what's going on, and say, look, this is easy. If income's greater than 85.5, then we're going to predict an owner with 91% probability, and that's bigger than the cutoff of 50%. If income is less than 85.5 and lot size is bigger than 20 and income is greater than 61.5, again, we're going to estimate ownership. And so you can see all of these rules are written out for each of the terminal nodes. There is some redundancy sometimes, and things can be simplified. For example, this last one says income less than 85.5, lot size less than 20, and lot size less than 17.6. So we really could just get rid of that part right there and say income less than 85.5 and lot size less than 17.6. The algorithm will go through and make all these leaves, and so maybe it's informative to be able to see that. But if you have the tree diagram, you can actually come down here and see this is that terminal node where lot size is less than 17.6, and you can see that it's redundant because if lot size is less than 17.6, then it's less than 20. So this brings us to the problem of overfitting, and you can see that if we continue to use this algorithm or this method, eventually we will recursively split the data down into single terminal nodes that have very few observations in them. You might call these leaves. Once the terminal node is pure, where everything has the same category, which doesn't always happen but can happen, then you would say that the tree is fully grown. And at that point, you're going to be overfitting the data. In other words, the noise is going to be showing up in the tree, and that's something that we want to avoid. And one way to do that is to look at the error rate in the validation set. So if we continue to split the training data based on the training data, we'll see that eventually there's going to be no error. We can get down to the point where we get a very small error rate or even no error. And so on the validation set, we can see when the error rate starts to rise. And once we hit that point, that means now we are fitting noise or randomness. So that's something that we want to avoid doing. And so for that reason, the validation data is going to be actually used to help pick the model. And because we're doing that, test data set is something that should also be employed when we're doing classification and regression trees. So this is one way to come up with a stopping rule. There are other ways. There's CHAID, CHAID, I guess you would say, and that's something that was around before CART, and it uses a statistical test to limit the tree growth. So in other words, as soon as the improvement is not statistically significant, then the stopping rule is employed, and the tree is not grown out any further. CART, on the other hand, kind of goes the other direction. It starts with a full-grown tree and then prunes it back. And the idea is to find the point at which the validation error begins to rise. So come back to this picture and find that point right there, and then continue to prune the tree back to get multiple models or trees. So one school of thought is to go back to, say, one standard deviation of the minimum. So maybe right here, you can see there's an inflection point. So the difference from here to here is not very much. So the simpler the model, typically we tend to do better. And so you could use this as a rule of thumb to say as soon as you get to within one standard deviation of the maximum, then use that model instead of this model out here, because this could be considerably more complex than the model here, and that just makes things harder to deal with. So one way to formally address that is to use the cost of complexity, and the cost of complexity is this formula here, where we say CC of T, so T represents the tree we're interested in. The cost of complexity is the proportion of the misclassified records in that tree plus a penalty for the size of the tree. So we have alpha times L of T, where L of T is the size of the tree and alpha is the factor that says how big the penalty is. So for a tree of a given size, we want to choose the one with the lowest cost of complexity, and we want to then do this for each size of the tree. This is the underlying idea with CART. JMP does things a little bit differently. It uses a combination of limiting tree growth and pruning the tree. And so the user would specify the minimum split size, or in other words, the minimum number of records in the terminal nodes. And then the validation data is used to maximize the R squared, which at the same time will minimize the error rate. In JMP, you would see this type of output for the personal loan data. Red is the validation data set. orange is the test data set, and so blue then would be the training data set. And you can see that this model goes up to 18 splits. And once it hits 18, it says, okay, that's enough. There's enough separation between the training, the test, and the validation data. So let's cut this back, prune it back to 8. And at that point, we have a maximum R² value on the validation set. What you should take from this is that JMP is not following the same procedure as is described in the textbook by looking at the misclassification rate on the validation set to pick the model or the competing models, and then looking to the test data set. Instead, it's using the R² on the validation data set. So there are lots of different ways to do CART models, and that's how JMP does it. So how do we measure impurity? Purity is a very important idea, and it basically just says how much of the terminal nodes are the same, or rather what proportion of the cases in a terminal node belong to a particular class. So we've got this Gini index, and there's another measure called entropy, and I'm not going to get into these too much. You can read about them in the textbook if you like. Turns out JMP does not use these. Instead, it uses the G² and the log-worth measure. So just to show you, there are lots of other ways to think about these things. Instead of using measures of impurity or purity, JMP uses measures of dissimilarity, the G² and sum of squares. This brings us to regression trees, which really are the same thing as classification trees, except for now we are trying to make predictions instead of classifications. So that means our outcome variables are going to be continuous, but the rule for splitting is going to be a little bit different. In this case, we're going to choose the split that maximizes the difference between the subgroup means, and that is measured as the sum of squared deviations. Once a terminal node is established, the prediction is just the average for the values in that node instead of a probability. Here we have Toyota Corolla prices. We have price on the y-axis, and we've got age on the x-axis. So whenever age is greater than or equal to 32, age is less than 32, we're going to have a split. And we're going to calculate the average age here and the average age here. And the split is going to be based on the difference, maximizing the difference between those two values. So why are trees good? First of all, they're easy to use and easy to understand. You can go and explain to anybody, technical or non-technical, what the rules mean, and they're based on the input variables, so pretty straightforward how to do that. The variables that are most important are the ones that show up first in the tree, and so this can be something that's used for variable selection, and there's no assumption of a statistical model, which means that you don't have to ever make any transformations of data or anything like that, and it works well even if you have missing data. What are the disadvantages? Well, if there's any structure, if your variables are closely related to each other, and that is going through to the output variable, then it's very difficult to capture that, because all we're making here are horizontal and vertical splits. Next week we'll talk about discriminant analysis, where we will, instead of making horizontal and vertical splits, we'll make diagonal splits. And this means that there's no way to capture interactions between variables. Now, one other disadvantage that's not listed here is that usually you need a lot of data to do this, and it is very computationally expensive. There are a couple of things you can do to improve on the classification and regression trees. The first one is called the bootstrap forests, and then boosted trees. Both of these are available in bootstrap forests are basically the combination of lots of classification and regression trees that are formed on random samples from the data, and then to get the prediction or the classification, then the final model is just the average of all of the trees that are produced with the bootstrapping. So bootstrapping is the notion of taking a random sample from the data and using that in order to come up with estimates, and then repeating that process over and over again. So that's bootstrapping. Boosted trees use a bunch of different simple trees that are used, that are fit with data on some of the predictors. So take a random sample of the predictor variables, fit a tree, take the residuals from that model, and use those in a new tree that is also based on a sample, a random sample of the predictor variables. Take the residuals from that and do it over and over and over again, and then the final boosted model is just the sum of all those models for the individual trees, and that has some implications in interpretability. CART methods are supposed to be transparent, easy to understand, but once you get into this boosted trees methodology, then you lose that ability, and it becomes more like the black box approach of the neural networks. So in summary, we've learned about classification and regression trees, otherwise called CART models, and these are usually very easy to understand and very easy to communicate to fellow workers and customers and anybody who's interested in what's going on. You can do both prediction and classification. We have a nice tree that is a graphical representation of a set of rules, and the trees must be pruned in order to avoid overfitting. That's again a big problem that we don't want to have happen. And finally, we don't have any assumptions about data structure, which makes us not rely on any sort of modeling assumptions, which is actually kind of nice. So that's all we've got for this video. We will see you in the next one.